This is the culmination of a couple of years of effort to really just sort of evaluate the opportunity for computer vision as a tool for salmon enumeration, both in the automation of counting from sonar video, but also in RGB video, so recorded at in-river weirs, like the image that you see here on the left of a coho salmon migrating through Kitwanga Weir. So across the global ocean, wild salmon face unprecedented changes in climate, rapid warming in marine ecosystems, freshwater disturbances ranging from floods and droughts. And this changing reality for wild salmon means that managers and conservationists need a new set of tools that allow us to track abundance much more in real time, given the failure of many forecast models for predicting salmon returns, and to adjust management regimes to respond to these changes in ecosystems and abundance. This is a time series of Skeena sockeye, but in many ways it's representative of trends for many species of wild salmon on the Pacific Rim and likely in the Atlantic as well. We see major regime shifts in their productivity with a decline in the early 1990s and increasing variability in productivity. So really, salmon are not behaving in the way that a generation before us would have predicted. And that means we need new tools that are relevant and capable of tracking this response. And another reality in British Columbia is just the vast and remote nature of this geography. In the Central Coast alone, there's more than 500 unique populations of wild salmon. And many of these watersheds have no road access, no power, very little infrastructure. And for decades, really for the entire history, the European history of people in British Columbia, that's challenged monitoring of salmon populations. And it's limited the set of tools that we have at our disposal to understand and track population trends. So computer vision is a tool that has been applied in a variety of arenas, everything from facial recognition to traffic monitoring. And what it involves is really automated object recognition and tracking. So the model is performing two tasks. The first being track this object, draw a bounding box around this object, and tell us when it has passed sort of through the frame. And in doing so, it then applies a count. And the second element of that is sort of classification. So it's saying, what type of object is this amongst the objects that I've learned from? And that's the important part of any AI is the training data. You probably have heard about ChatGPT. You've probably heard about Google Bard. Tech companies are spending literally billions of dollars worth of computing power and person time in feeding training data to these large language models. And the more data that you feed these models, the more powerful they become because they have much more comprehensive understanding of the objects that they're being asked to identify. And we know that with proper training data and with the high enough volume of training data, these computer vision models can achieve extremely high reliability, often exceeding the reliability of a human reviewer and in a much more timely fashion. So to give you a sense, last year, we ran a computer vision model on full season data from the Bear River Weir, which I'll show you some pictures of the Bear River Weir in a little bit. That data was 4 months of continuous video, and it took 4 days for a computer vision model to provide a count for that entire season. That task typically takes technicians with the Skeena Fish Commission about 2.5 months of data review. So this is a tool that can expedite data review for whole season data, or it can provide continuous analysis of data as it's generated. And really, in scoping this project, we realized there are increasing number of tools leveraging AI in conservation, but it really has been overlooked as a tool for salmon monitoring. In a lot of cases, we still have people sitting, on the back of a weir with a traditional sort of tallywhacker clicker, watching fish go through a box. And maybe that person likes that job, or maybe that person would like to be doing a more interesting and engaging job that allows them to maximize the benefits of their labor. So we really do believe that automated analysis of video and sonar can support, broader monitoring coverage, can allow monitoring organizations with limited resources to maximize the benefit of their employees' time. And most importantly, it can provide in-season information to support climate resilient fisheries. So I sort of covered some of these benefits, but just to review, we're looking to reduce staff time and the costs of reviewing video and sonar, and this need emerged out of our own work. So I work closely with the Heiltsuk Nation, a variety of other First Nations, building weirs for salmon population monitoring. And one thing we realized is, these nations have limited technical staff, typically between 2 and 5 people that go out and operate their monitoring infrastructure. Those people have an immense number of skills, but they don't necessarily want to sit in front of a computer all winter or fall reviewing video data from the summer when they could be doing other things. This information is also beginning to empower decision makers with real-time info, and we're sort of scoping right now how we want to deliver that data pipeline. Are we performing analysis on the edge, which means are we performing computer vision analysis on computers that are on site, or are we streaming data out via Starlink or some other satellite internet connection for analysis in the cloud? We know given climate variability and unpredictable returns of salmon that we need to be able to support in-season management that reduces risks. And risk reduction is a big part of this. Salmon are very resilient to harvest, but in a year when you're not meeting your escapement goal, harvest can be a source of sort of sustained downward pressure on the population. I also like to emphasize that it's also about creating opportunities for fishing. So, we've had a downward trend, but we've also had a lot of unpredicted sort of booms in salmon abundance over the last 2 decades on the West Coast. And in many cases, management agencies were ill prepared for those upticks in abundance, and the fishery weren't able to mobilize in time to capture that opportunity, largely because the information isn't available in a timely fashion to inform that management decision. And then a big part of this BC context is really the reconciliation work being done between First Nations and the federal government and the provincial government, which is creating sort of a new era of co-governance in fishery management, and where First Nations are taking on a much greater role in decision making, in population monitoring. And nations want to bring their own data to the table. They want to be able to sort of have the agency and authority that comes along with owning the data. And so this has really coincided with the reemergence of First Nation leadership and the reemergence of weir building, which was actually banned in British Columbia in the 1870s by the colonial government as they sought to sort of push First Nations people out of their subsistence lifeways and into the workforce for the cannery operators, and to really consolidate control of the fishery resource in the hands of the commercial fishery. And then, another exciting element of this is that there's potential for autonomous counting at remote sites. And the Bear River Weir, which I alluded to earlier, is in fact an autonomous weir running entirely on an off-grid power system and generating an entire year's worth of information with only about 2 visits from staff. So in a remote region like the Skeena River, where, to get to a lot of these rivers costs $5,000 or $8,000 worth of helicopter time, you don't want to be visiting it every day. So we need to figure out how are we going to monitor these populations in a way that produces high quality full season data without breaking the bank, essentially. I also want to note, like, this is a very diverse project team. I sort of am speaking for the project right now. I'm the PI on the project, but I'm not a computer scientist. I'm not an app developer, and I actually don't hold the grant. The grant is held by the Pacific Salmon Foundation, where I was a postdoc 4 years ago when we got the initial seed funding for this work. So there's a lot of people who have put time into this work, and I'm very grateful for their efforts and their contributions and their ongoing partners in this work as we look to build on this foundation and really amplify the impact. So if you've seen the paper that we produced, it really is sort of a reflection of this phase 1 of the project. So the question was, can we develop a computer vision model that works, that can count salmon in a reliable enough fashion, or at least start to count salmon in a reliable enough fashion to be feasible as a management tool? And so we worked with 5 different First Nations, Simon Fraser University, and the Pacific Salmon Foundation to build a computer vision model for both video and sonar monitoring. And at the time that we published this paper, the video monitoring module was very much more advanced with a lot more training data. And so that was really the focus of this publication. So far, at the time of the publication, we had about 750,000 frames of data. That number is now more than tripled. And that data came from 2 sites, the Kitwanga Weir in the sort of middle Skeena, run by the Gitniao Fishery Authority, and the Bear River Weir run by the Skeena Fish Commission. And so those data were annotated by technicians with fish attributes, species being the most important, but also sex, hatchery, clip status, the presence of visible injuries. And then those data were fed into a computer vision model. A subset of the data were withheld, and then the model, having been trained, was tested and evaluated on that withheld data. So it's almost like any statistical method where you sort of withhold a subset of data and then refit the model to that data to see how it performs. And again, I want to give a really big shout out to our project partners. They've invested immensely in their own weir infrastructure, and they're doing that for their own reasons. But they very generously provided us with, multitudes of data, years worth of continuous video monitoring information that they've spent, hundreds of thousands, if not millions of dollars to generate. And so this is a picture of the Kitwanga weir and the crew from GFA. And, I just want to give a big shout out to Mark Cleveland and his team. They're a world-class monitoring organization in the Skeena River, and it would be a very different place without their efforts. This is a picture of the other project site, the Bear River Autonomous Weir. So this is in the Upper Skeena. It's a tributary of the Sustut. If you like steelhead fishing, you may have heard of the Sustut before. The Bear River Junction is actually one of the best steelhead pools on the planet. So this is an incredibly important river, not just for steelhead, but also for Chinook, for sockeye salmon. And interestingly, DFO has performed population monitoring for sockeye in the sort of lakeshore and tributaries of this river for 50 years, and they do it via helicopter flights. So they basically fly over, they count the fish that they observe, and then they make some expansion, usually about 4 times what they count, which is an arbitrary number that's never been evaluated. And then that is the escapement estimate for the Bear River. Well, this project monitored sockeye salmon for the entire season, and they found that there was actually about 5 times more sockeye than the DFO estimate, likely because a lot of fish either weren't visible to the survey or were spawning in areas that weren't being counted. So this gives you a sense of how important a sort of a comprehensive full season information can be for monitoring and management. We used a software called Computer Vision Annotation for training, and there's a few different annotation softwares, but essentially this allows technicians to sort of manually apply labels to fish by drawing bounding boxes, and then you can see these different attributes that the technicians are filling in. Those attributes are all then recognizable by the computer vision model. And a really neat thing is that the sort of computer science team set us up with a tracking algorithm. So the technicians are able to label the first frame of a video, and then essentially those labels are applied to the fish throughout all of the frames associated with that video. So you can imagine an individual video might have 4,000 frames or 2,000 frames. You don't want to have to apply an annotation label to each of those frames, but the computer actually sort of ingests that information as individual frames. So each video generates a lot of quality information for the computer vision model. A total of 530,000 annotations were generated from Kitwanga and Bear River and were used to train this initial set of models. Now, the models were built on an open source YOLO architecture. YOLO stands for You Only Look Once, and it's an open source family of models that are coded in Python, and they're available online. So anybody can adapt a YOLO model to their own computer vision challenge. And of course, building a computer vision model is much more than having an underlying model architecture, but it's a great head start. And so the computer science team built these 2 separate YOLO models, which I alluded to earlier, one being a multi-object tracker, which allows the computer to track multiple fish moving through the box and determine when they've passed upstream of the outlet of the video box, and a species detector, which is really doing the sort of identification of species for counting. As I alluded to before, models are then trained on these data. Training typically takes about a day or maybe 2 days, depending on the volume of training data. And then that trained model is actually stored. Imagine an MP3 file. When you would open an MP3 file, in the old days, you could open it in a text viewer and you would see sort of a jumbled set of symbols. But when you move that MP3 file into a media player, all of a sudden, that player understands the information contained in that file. A computer vision model is very much the same in the sense that you can export a trained model, you can save a trained model, and you can actually apply that trained model to new data. So as a part of this, we're storing trained computer vision models online. They're available through our GitHub. Of course, we haven't trained it on Atlantic salmon yet, but practitioners over time will be able to download different pre-trained models and apply them to their own data sets. And I'll get into what that looks like a little bit going forward. Now, one exciting piece of this is that YOLO, there's a variety of YOLO models. We're now on YOLO V8. And the neat thing about the YOLO V8 model is that it can actually run both the object tracking and species classification at the same time. So that really dramatically reduces the computing power and the sort of complexity of the analysis, because if you can package the entire system in a single model, it gets you much closer to being able to run this analysis on the edge, which means on the site on less powerful computers. Currently we're running this analysis on a supercluster at Simon Fraser University. Well, not every partner is going to have access to a supercluster, and ultimately that can't be the bottleneck. So we're trying to figure out ways to package this model in a way that it's small enough to be run on the site and that the outputs of those analyses are reliable. So we tested 4 different models leveraging this pre-existing YOLO model architecture, and then we evaluated each model's performance using several metrics. One metric being the mean average precision score, which is essentially a balance of the correct and incorrect identifications for each video. A species-specific map score, which is essentially the same metric but applied at the level of individual species to let us know, is the model performing better for some species than others? What might be reasons behind that? Is it just a lack of training data, or are these species really a bigger challenge? You can imagine Chinook salmon, for example. They have many different ages at maturity. There are Jack Chinook salmon, much like the grilse, but there are also 5 ocean winter Chinook salmon that are 40 or 50 pounds. They look really different to a computer vision model. So we needed to understand these are all one object class. And likewise, pink salmon have extreme sexual dimorphism. So a female Chinook, pink salmon rather, looks very different than a male pink salmon, which have these large humps and extended kypes and really look like a totally different critter. And then we generated these confusion matrices, which are also presented in the paper. And what they tell us is, when is a species being misidentified? What does the model think it is? And that's a way to sort of gain some insights into what are the challenges the model's confronting. Because one of the main challenges with AI is you don't actually know why or how it arrives at the decision that it arrives at. It's not telling you. You just know if it's working or if it's not working. And so these confusion matrices are a way to generate a little bit more insight into the performance of the model and what are some of the limiting factors there. So this table on the left, and I apologize, it's a fairly texty slide here, but what this shows is the test set. So what data were we testing? And then this shows models that were trained on different data sets. So this is the Bear River test set. These are data that were withheld for the Bear River. This is the Kitwanga, and then this is a combined Kitwanga and Bear test set. Each of these lines is a different YOLO model that was trained for this project. And then this is their score when trained on these specific data sets. So you can see if you're just trained on Bear River data, you tend to have lower performance. If you're just trained on Kitwanga data, you have slightly higher performance, but still not optimal performance. And if you're trained on both Kitwanga and Bear, these are the models that generated the highest performance for us. So you can see for the Bear River test set, a model trained on both Kitwanga and Bear achieved a model-wide map score of 60.3%. For the Kitwanga test set, a model trained on Kit and Bear achieved 70% model-wide map score. And then for a test set comprised of both, a model trained on both achieved a 67.6% map score. So we're not quite to the place where we can say, let's just go out and monitor for a full season. The computer vision is going to do as well as a person, but it's telling us that we're moving in the right direction. And one of the challenges is we had more training data for Kitwanga than we did for Bear, which may explain the sort of difference between these two systems in terms of performance. When we look at this at a species level, we can see for some of our focal species, particularly coho and sockeye, model performance is really already approaching levels that would be consistent with us being comfortable with applying this for in-season monitoring and management. And so a lot of this has to do with those being some of the more abundant species in the training data, but it may also have to do with them being sort of more distinct and the computer vision's ability to recognize those as distinct classifications. Importantly, YOLO V6, which was actually the highest performing model in a lot of cases, doesn't report class-specific map values. So that is a limiting factor for that specific generation of the YOLO model. And I noted earlier, but Chinook and pink were more challenging for the model. I think for Chinook, that was largely due to a dearth of data and, again, the sort of distinct age classes that Chinook return at. We have separated out Jack Chinook now as a distinct class because they are so morphologically distinct. They're so much smaller than a sort of normal adult Chinook. So we want the model to recognize them as Chinook, but we're telling it Jack Chinook is a different classification, and we think that can improve the performance. And we're also now using the classifiers on their sex as a distinct sort of way of modeling differences in pink salmon, because we know that sexual dimorphism is extremely important. So, what are the next steps? We're really fortunate. We've received a second round of funding from the Government of Canada and British Columbia to advance this work over the next 3 years. And so an immediate priority for us is generating more training data, not just from Kitwanga and Bear, but from the whole constellation of 10 projects that we're working with throughout north and central coast of BC. And so we're already underway with that. I think we've got about 1.5 or 2 million new training videos annotated, and we're also, investing a lot in annotation of sonar data. That was really the gap for us in the first round of sonar model development, was that we'd only had about 100,000 frames. And, while video projects, there is more sort of project to project variation, there is a fair level of variation in sonar sites and how far the beam is being cast, and that creates important differences in sort of how the data looks to the computer. So we know that we need sort of this large generalizable data set that allows the computer to be capable of being applied in new places sort of rapidly and functioning at a high level. So that's called the sort of generalization or the generality of the model. We need to have enough data that it can be applied at a new site and work, right out of the gate. Previously we'd had sort of technicians in the lab doing this, and that when you're working with undergrad technicians at a university, it can be a slow process. People come for a month or two, they learn the skills, and then nope, they've got too many classes this term to do annotation. So we said let's professionalize this effort a little bit, and we've contracted with an organization called Digital Divide Data to really maximize the rate of annotation and the output of annotated data, and that's been a huge upgrade in the project. Another really cool thing that I'm excited about, and it's quite important for the video module of this model, is that we've worked with partners to standardize our video system and our trap box design. So this was a design originally developed by Gitniao Fishery Authority, adopted by the Skeena Fish Commission, now adopted by DFO as their standard for weir video monitoring. And what we're doing is essentially creating a controlled environment. So the fewer variables that the model has to contend with, the less variable that the data being generated is, the more likely it is to perform reliably at new sites as you sort of implement video monitoring. So what you see here on the right is this, fish migration box. The fish are moving upstream, passing through this camera box. There's a white background behind the fish. There's some sort of overhead lights illuminating the box with fairly even light. And then there's a camera behind a plexiglass window inside of this little sort of V area here, which records their continuous video. And these boxes we have a fabricator in the Skeena watershed that has now built about probably 25 or 30 of these boxes, and they're all over the BC coast. And what that means is that we're generating really standardized data, both for training and annotation, but also for ongoing monitoring, so that we know we can reliably produce results for partners. And another thing that we've been doing is really sort of trying to design a standardized system for power, for cameras, and for network infrastructure. So how do we generate this video? How do we store the video? How do we then sort of transmit it and analyze it on site? And what you can see here on the right, this is our sort of standard video system setup now. You've got your network switch, which is essentially taking the information that's coming from the cameras. That information comes into these little Jetson Nanos, which are sort of microcomputers that are commonly used in AI applications now. And then that information goes into the network switch. This other microcomputer called the Raspberry Pi is processing it using its image driver, and then it's storing those processed images onto an external SSD hard drive. Another important component of this system you can see here, this is the Starlink network router. So we've got Starlink at each of these sites. Importantly, that allows us to stream the data off the site at a relatively reasonable cost and a pretty high bandwidth given the remote nature of these sites. But it also allows us to monitor the site continuously. If it's a 2-hour boat ride from one of these remote communities to this monitoring site, they're going to spend $400 in fuel just getting out there to check on it. And so the ability to check on these sites remotely to make sure the weir is functioning as expected, that fish are able to pass through the box, etc., and be able to do that without spending all that fuel is an important sort of upgrade in our monitoring systems overall. So yeah, I've sort of alluded to this, but we're now entering phase 2 of this project, and we're building out weir monitoring projects really across the northern central coast of BC with a variety of partners that includes the Kitasoo First Nation. You can see their new weir at Quaqua Lake here. This weir was built with the intention of monitoring a sockeye population that's extremely important for their community's food fisheries. We're also working with the Wiikiano First Nation on their sonar project, as well as the Nuhawk Nation. And we're working with Gitgat and Taku River Tlingit, in addition to the other partners that I mentioned before. And, while a big thrust of this project is to build and apply computer vision, we also know that we need to support infrastructure and capacity for these weir and sonar monitoring programs. So a large chunk of the money that we got through this grant is actually going directly to partner First Nations to support their staff, to support their infrastructure investments, and to really sort of build out a system of better monitoring programs across the north and central coast of BC. And we've been able to leverage this grant support to get additional funding for partners like Gitgat, Heltzik, and the Kitasoo Stewardship Authority to build and invest in these programs. And we're really moving towards applying these computer vision tools in season. This will be the first year that we attempt sort of a true in-season computer vision analysis. And I think it's going to be, no doubt will be a learning experience, but we've learned a lot in the last several years, and I think we're quite prepared now to deliver on that vision. So the goal long-term is, rapid in-season data delivery near real time, and then visualization tools, data export, data checking tools. And I think I have a slide a little bit later to talk about that element of it, but we want managers to have seamless integration of data into management decisions, because we can't be putting hurdles in people's way. Most of these folks, they don't code in Python, they may not code at all. They need tools that are sort of drag and drop, click, plug and play tools that are ready to be used by anybody with sort of a normal set of computer literacy skills. And this is a part that really excites me. So we're developing a web app that allows user-led computer vision analysis. And what this will do, it means that if you don't have the skill to code in Python, I don't have skills to code in Python. So thank God for the grad students at Simon Fraser that have built this computer vision model, but it will allow people that don't have coding skills to essentially access pre-trained computer vision models and then perform their analysis, see their data exported, and really kind of have access to that data in a much more timely fashion. And we're working with a diverse team on that, working with folks at an organization called Area that do aerial drone surveys and are training in AI. So this AI will have 3 modules. It'll have an aerial photography module that automates counting and species ID from drone photos. It'll have a sonar module, and it will have a video module. So we're trying to build tools across the whole suite of sort of escapement monitoring programs that can benefit from computer vision. And as I mentioned, we're experimenting with edge and cloud computing during the summer. So one option being running the computer vision model on the site, having that model then export, a CSV or some sort of data table with a summary of counts, and that being the data that's used in season. The challenge with that is that this is going to be a smaller model, a model that has less computational power behind it. So we want to evaluate the performance of this smaller, more compact model with the sort of full suite of model tools that are accessible to us in the cloud. So these projects will be also streaming clips of their data, motion detected clips of the data out to the cloud, and then performing that analysis, on a GPU hosted by somebody like, Amazon or another service provider that has powerful GPUs that can be accessed via cloud computing. And I think a lot of the sort of goal of this is not only to sort of provide timely analysis, but also to provide really important functionality for these users. So one of the main functionalities we want to be able to build into the app is that users can review and correct their own data. We know that computer vision models aren't going to be perfect. Probably for a long time, a smart person is going to be smarter than a computer vision model. And so we want to allow them to correct their data, have that correction be automatically uploaded into the new updated data set, and have that be the new count. We also are creating data visualization tools where managers can look at an individual project or across all their suite of projects and understand, how is the run coming in relative to our expectations, to compare that to long-term data, and even to visualize their escapement data alongside temperature and river flow data, because we know that temperature and flow can be key drivers of salmon migration timing. And so that's a key element of sort of informing their understanding more broadly. And then another really exciting element of this, because we've spent a lot of money generating video annotations, is that this app will actually generate annotations automatically. So if a user confirms the species class and the different classifiers that have been applied by the computer vision model to the video that they're reviewing, that then becomes an annotation which is stored for later model training. So as users, log into the web app and they review their data, maybe 10% of their full season data is being reviewed manually. That 10% becomes future training data that then iteratively makes this model better and better over time, so that we can maximize the performance and the value of the tool. And as I mentioned, we're launching a beta version in 2024, but we really have, built this partnership with an eye towards a subscriber model in future years. So, we're all NGOs, we're all conservation practitioners. We're not a tech company in Silicon Valley, and frankly, I don't think they're the right people to take this challenge on. This isn't scalable at that level, but I think there are no doubt hundreds of salmon monitoring projects in North America and likely more throughout the world that could benefit from this technology. And so what we really want to do is create a tool where a user can come to us and say, we want to build computer vision model tools, or we want to apply computer vision model tools. Let's get a training data set going, and then we can access the app. We can continue to improve on the performance of the model, and we can rely on applying it this way year after year. And so, the sonar model, I wanted to mention this because I understand that quite a few people are applying sonar in Europe. And I think, the sonar model really is potentially immediately transferable to Atlantic salmon. Our sonar model doesn't do species identification at present because it's quite hard to identify a species from a sonar image, which is, as you probably know, a little sort of blip of light moving across the screen. So an Atlantic salmon likely looks very similar to a steelhead or a sockeye moving past a sonar unit. And so I think there is, potential to apply that sonar model in the context of Atlantic salmon in a much more near-term sense. And then, developing training data is not an insurmountable hurdle for the video component of this. And I'm very interested long-term in the possibility of sort of building an Atlantic salmon specific training data set for that video model, and then having that pre-trained Atlantic salmon video model stored on the app. So if you're a user who has an account and wants to analyze, full season video weir data on an Atlantic salmon population, you just tell the app, hey, I'm doing Atlantic salmon. I want to use that pre-trained Atlantic salmon model, and then that is the tool that's going to be applied to your data set. So, we can sort of build subcomponents to this web app as we go and as the need arises. And I think I often conclude with this slide just because I'm so blown away by the sort of pre-colonial engineering feat that it encompasses. This is Yelm Jim's fish weir on the Puyallup River and sometime around the 1880s in Washington State. And this really, emphasizes to me the sophistication of salmon management that came before, colonization of North America. And that these systems, they persisted for thousands of years. People were building weirs at least 6,000 years ago, probably more. I know that weirs are technology that's not unique to North America. They've been found in Europe, they've been found in Asia. And I think, a lot of the challenges that humanity faces today involves both sort of developing new technologies, but also learning from the past and saying, where are the examples, of excellence in human civilization and human societies where people were able to strike a bargain with nature or create a long-term sustainable system for managing resources. And I don't think we've cracked that nut yet, in the modern sort of colonial capitalist context. And so this is really, I think, an exciting example of sort of braiding this ancient tool with cutting-edge computer vision technology and to power resilient fisheries going forward. So I think that's my last slide. And with that, I'll wrap it up and just open the floor to anybody that might have a question.